Hey everybody, welcome back. I know it's been a little while. I apologize for that. The Thanksgiving holiday break from work for me really threw me out of my normal routine. But we're getting back into it with some machine learning, which I promise you will not disappoint. It will seem like worth the wait here in another couple weeks when we really get into the meat of it. So today, I really just want to give an overview of machine learning, kind of some background, what it is, go over some key terminology. Unfortunately, it's probably going to feel a little bit like a lecture from when you were back in school, just because there's a lot of information and a lot of different things that could be classified as machine learning, so to speak. And depending on the different types of data you have, is going to drive what types of algorithms you use. There's just a lot of key terminology I want to go over before we really get in and start doing it, just to make sure everyone can have a baseline understanding of what we're talking about here. So, to start us off, we have what is machine learning? Now, machine learning is going to fall within the broader umbrella of artificial intelligence. Within machine learning, you'll be able to look at neural networks as kind of a separate subdivision of machine learning. And then within neural networks, you'll have deep learning. And that's where you get into the different types of algorithms that can drive, driving cars, like autonomous vehicles, Tesla. That type stuff's going to be more in the deep learning. For machine learning, you can think of it as just writing your code and the algorithms you use allow the computer, because we want to think of computer as machine here, so really computer learning, it allows the machine to learn and get better without any further changes from yourself. So think of what we've done so far. We have like our web scraping, okay? So we go online, we write our web scraping code, and we go get our stats. It doesn't matter how many times we run that, it's going to do the exact same thing every single time. No matter how many times you pull the data, no matter how much the data changes, it pulls that data from that location. If it cannot access that location, it just stops and breaks, as several of you have found out in your comments that I try to respond to there. You hit an error and it says it can't find the thing you're looking for. No matter how many times you run it, it's going to give you that error that it can't find it. It's not improving itself. It's not getting any better. It's doing exactly what you say to do when you say to do it. Machine learning is going to be different from that because it's going to allow itself to get better based on basically a time function or a usage function. The more it gets used, the more it can learn and the better it gets. So think of, like, we want to predict fantasy point output, right? So in theory, the bigger data set that it has to train off of, the better predictions it's going to be, because the longer it runs, the better it gets. And that's so it. I know machine learning just kind of seems like this big, broad, vague term that a whole bunch of things fall under, and it's kind of true. But an easy way to think of it is just that it allows your algorithm to get better without you changing the algorithm. That's pretty much it. So moving on from there, we have two different types of data that we can perform machine learning on. Number one is going to be continuous data. Number two is going to be discrete data. And anybody without a pretty significant mathematical background or statistics background, those terms may not mean much to you, and that's perfectly fine. So some basic background with coming from a mathematics point of view. You have different types of numbers. You have rational numbers, you have real numbers, you have imaginary numbers. You've got like different number scales to look at. What continuous data is going to be. Actually, let me back up for a second. To help explain this, I forget the name. There's an old theorem from like ancient Greece or Rome. Theorem about... Whoa. distance between, there we go. So let's look what it is. The area of calculus. What was the, there's some famous Zeno's paradox. That's probably it. I'm going to guess it's Zeno's paradox. Sorry for going off on a tangent here. I don't know if it's Zeno's paradox. I'm tired of looking for it. So let me just explain it to you. So let me open up my handy dandy paint here. Basically, what I'm thinking of is you have A and B, okay? And forgive my terrible drawing. I'm even worse with pen and paper, if you can believe that. So what this theorem is stating is that essentially it's logically impossible to ever get from point A to point B, because no matter where those 2 points are, you can mark a point as halfway between A and B. Okay, so if you're getting to A to B, you have to get halfway there. Between A and this point, there's another point that's halfway between those points, and so on and so on and so on. So any 2 given points, there is a location that is halfway between them. And the fact that you can always be halfway between the other point, you're never actually going to make it to the next point. So if we think of discrete values as A and B, and we think of continuous values as all of these 1/2s going through it. So discrete data is that, you go from point A to point B. Those are just 2 things to choose from. It doesn't, an easy way to think would be like integers, like 1, 2, 3, 4, 5. And a continuous number would be anything between 1 and 5. It doesn't have to be an integer. It doesn't have to be to 1 decimal point, to 2 decimal points. It could be any value between A and B. Theoretically, an infinite number of values between A and B. So that's going to be the main difference there. And I kind of wrote it out here. I wish I would have thought of that theorem before when I was writing this up, because that would have been a much better example. But anyways, continuous data that can take any value in a range. So any value between 0 and 1. 0.5, 0.6453, 0.45789362, 148. That would be what we're looking at for fantasy points, okay? Because we don't want to limit ourselves to just a point, just a range. It has to be, 1, 2, 3, 4, 5 up to 150. Anything, because we're going to get pretty exact with our outputs. Now, obviously, it's going to be, whole points, maybe half points, depending on how the scoring system is. So it's not really going to be continuous data, but that's how we're going to look at it. Discrete data is going to be a specific set of values. So 0 or 1 or 2 or 3. Like, you define how many values there are. The reason why we're not going to be using the discrete algorithms is, while technically, yes, it is going to be a pretty limited set of values that our fantasy output can be. But what happens is you get limited to the range of values of your data set that you feed in. So one thing that I had done, like a year and a half ago probably, was working on some golf data sets, doing something similar to this. And I was experimenting with some discrete algorithms using like golf scores. It was like, negative 15 is their score for the tournament. Like, I can just do like negative 15, 14, looking at that, not thinking about the bigger picture of what I was trying to accomplish, and just looking at the data I had. And what that meant is that I was trying to factor in like how, like a golfer, how they perform in certain scenarios, and then predict how they'd perform on that course. The problem is it would never predict a golfer outside of the data set that I fed it. So it would give me like a much more narrow output range and a whole bunch of golfers tied for the same stroke count, essentially. So what I use discrete data for NBA analytics is to establish player archetypes. So if any of you have played like 2K or anything, you'll get like, your player type, 3 and D, like post scorer, post defender, perimeter defender, floor general, superstar, like those types of distinguishing play styles. And then I will take that and feed those results into my continuous data set and run some regression algorithms. And that's one of the methods I use to help get fantasy output. So within each of those data types, you're going to have different types of machine learning to use. So supervised learning and unsupervised learning are going to be the two main, really the only two distinctions there. So supervised learning is when you're searching for a specific outcome, i.e. fantasy point production. What that means is you have a data set with the answer, essentially, and you're trying to predict future instances, that same answer for new input that we don't have an answer for yet. So what you'll get there is just like all our box scores, or what would be a different example for that? I don't know. Anyways, supervised learning, I already explained it. Unsupervised learning is going to be when you have a large data set and you don't really have a specific endpoint in mind, right? So that's when you're more looking for insights or patterns in the data, like you have your big data set and you just kind of want to know what's there. You're not entirely sure, you're just kind of poking and prodding. That's more like exploratory data analysis. That would be the player archetypes, because I have all the data and I just feed it in and I'll do through some analysis define how many groups I want it to separate into, and then it takes that n-dimensional data and separates it into a finite number of groups as defined by me. I don't define what each of those groups is. I don't go in and say I want these stats as a 3-and-D player, these stats as a post scorer. I don't do any of that. You just tell it the number of groupings you want and the data you want it to make groups from, and it does it for you. And then you can go look at the results and kind of see, okay, that was good, that was bad, take this data out, add this data in. I need more groups, I need less groups. That's all stuff you do after the fact. Examples of the types of algorithms used for each of those and for the data type. So for supervised learning, for continuous data, we have regression, typically linear regression. That's what we're going to use to predict fantasy points. And for discrete data, we have classification and categorization. We're probably not going to do much of that with the daily fantasy stuff, but that is where you'll get like image classification, or the if you have handwritten notes and you want like computer vision to be able to translate that and bring it up on the computer, things like that. And again, that you need a training data set. So in order to do that, for image classification, you're going to need a bunch of images with the correct classification on it, and then it'll train off of that, and then you feed it new images, and it will correctly drop them into the right bucket, theoretically. Unsupervised learning for continuous data is dimensionality reduction. So what that's going to do is, so going back to my terrible drawings here, where is my cursor? Oh, way down there. Okay. So if we look at like a normal XY plot, that's in 2 dimensions, right? We go over X points, up Y points, right? If we want to do 3-dimensional, I'm not going to force you to see me try to plot in 3 dimensions because I'm terrible at it. But 3-dimensional plots, you can kind of look at it and engage trends and patterns and do your groupings your own. Obviously for X, Y, and 2 dimensions, it's pretty easy. Like I can look at that and say, oh, we're going to break right there. That's a good break point. Or maybe we break there, Either way, in 2 dimensions, the human eye, you can look at it and you can distinguish those things. 3 dimensions, if it's a good plot and there's not a ton of data points, you probably can. But if it gets cluttered, it's going to be very difficult in 3D. 4 dimensions, 5 dimensions, 6 dimensions, 7 dimensions, which doesn't really, it's not really comprehensible for us just to like imagine, because what in the world is 7 dimensions, right? But what all dimensionality is the number of variables you have, because for x and y there's 2 variables. If we want to throw in a z variable, that's a 3 variables, 3 dimensions. 4 dimensions is 4 variables. Throw in time. 5 dimensions, 5 variables. 6 variables, 7 variables. So if you're looking at advanced stats in the NBA, you might want to use 20, 30, 40 variables to look at these things, and there's no way that you're going to be able to identify those. So dimensionality reduction will take those and it will kind of group, mold, combine, and reduce so you can plot them on an XY axis with just 2 variables, or an XYZ axis with 3. That's what dimensionality reduction is going to be referring to. And we probably are, I mean, we might do a little bit of it, but I really don't do it that much. I don't do it very often. So we probably won't do it right away. That might be something we get to later if there's some interest, but not right now. And discrete data unsupervised learning is going to be clustering algorithms. That's going to be where we identify our player archetypes. And what that's going to do is you feed it the data and it'll pick, so it'll randomly select some points. And depending on how you do it, I guess, we have nearest neighbor, k-means. There's a couple different methods. Nearest neighbor is the easiest to understand because it'll randomly select starting points, and then it will simply say, okay, the closest point to this is in this group, closest point to that is in that group, and keep going there and selecting the closest point to the new center of that area. Let me see if I can show that on Paint without looking too terrible. There, it's much faster. Okay. So, I'm just going to put a whole bunch of dots here. I know some of them are dashes, some are dots. I'm impatient, sorry. So, what this is going to do is, let's say we've selected this as a starting point for one, this is a starting point for another. It's going to take it and it's going to say, okay, you're my nearest neighbor. Here's my new center. You're my nearest neighbor. Here's my new center. And then we come back and we say, okay, you're my nearest neighbor. So now we have like this little triangle here, and here's our new center. Didn't want that. And then say, you're my nearest neighbor. So now we have this little shape, new center. And it keeps going that way, selecting the nearest neighbor and adding it to that grouping until you kind of meet up, and then it'll define, which is going to be better and which is going to be worse. And that's really all we have for this. We're going to get into unsupervised learning first, because it'll, we want to have our player archetype definitions before we move into the actual prediction. So we're going to do some basics with the unsupervised learning clustering algorithms to kind of get a feel for with some actual coding examples, and then we'll dive into the actual NBA stats. So that's going to be it for today. As always, if you like the content, please subscribe, like, hit the notification bell. If you have anything that you'd like to see machine learning related that I didn't mention today, let me know down in the comments, and I will definitely work on getting it into this video series. Thanks, everyone. See you next time.